So, hello everybody. So, this lecture will be about visualization and especially with a special cool tool called ParaView, which you will be able to view your results in when this project has been completed. So, we will be using the ParaView software to kind of look at the stresses or the flows or the pressure heights or temperatures. And we will be able to generate from Python generate special files that you can use with ParaView. So I want to give an overview of ParaView first. So ParaView is a tool that has been available for a very long time, and it can handle visualizations from small scale to large scale, and even to running over multiple servers. So it's a tool that can handle most of any visualization you can think about. So you will have the slides here, and there are more slides than I will cover in the talk. You can go through them if you want. They are open source, so I'm using them. These have been developed by the developers of ParaView. There's a company called Kitware. So first I will just go through basic introduction of visualization, and then also basic usage of the software, and also how you visualize certain kind of models and the basic workflow of the application. So as I said before, it's a tool for visualization. It's open source. It can be run on Windows, Mac, and Linux. It can also be run on large HPC computers like we have at Lunark. So you can do so many of the operations you do to kind of cut data in half and visualization algorithms can be done on multiple computers at the same time. It has a very open and intuitive user interface. It can be non-intuitive if you don't understand the workflow, but when you understand the workflow, it's extremely easy to use. It also has an extensible modular architecture, so you can add plugins to it. You can interface it with Python. It has also a built-in Python interpreter. And every model you design, you can export as a Python script as well. And of course, you can buy commercial methods and support, but that's probably for a later time. So here are some images that are all done by ParaView. So you can see they're quite diverse, and they can also be quite large. So it's very common task to visualize finite element models with millions of degrees of freedom. That's no big problem for ParaView. So our 2D problems will kind of not pose a big challenge for ParaView. Yeah, you can see it's used by both academic, government, and commercial institutions. It's one of the most downloaded, I would say, visualization applications overall. It has a lot of awards as well. So you can see some of the achievements they have been doing with this. So 6 billion structured cells, 250 million unstructured cells, and also 6.3 billion unstructured cells in Catalyst. This is a special version of this tool. So it's kind of, you can go from really small to really, really large with this. ParaView is built on a library, a C++ library called Pyvtk, which stands for Visualization Toolkit. And it's a really large C++ library encapsulating almost all visualization algorithms you can find. So never kind of, before you develop your own visualization tools, look into the plugins of ParaView. You will probably find a plugin that can do certain kind of visualization. On top of that, you can run it as a server, so you can have it run on multiple servers on a big computer as a backend, and then you have a user interface that calls on this backend to do the computation. And what we are going to do in this course is a single application which you can download, which contains all of these layers. It's the ParaView client, which is the user interface you will see today. And there is also a built into this distribution, there's also something called PV-Python, which is a ParaView Python interpreter, which has all the extensions of ParaView built in, so you can run your visualization scripts directly from this Python prompt. You will not be calling ParaView directly in this course. So what we will do is we will generate input files for ParaView, which you can open and do your visualization in. You see some development here. So it has been developed since the early 2000s. VTK existed before this, the visualization toolkit. So this is a kind of a user interface development that was built on top of this VTK library. And also the latest versions of this tool, now you can use VR as well to display. You can go into the models and look at them and hold them in your hands and kind of get a more direct approach to visualization as well. Let's kind of skip this. So what is the basics of visualization? So your problem when you're running your application now, you have seen you generate a lot of numbers, which are results. And somehow these numbers are field of data that you kind of want to get a better feel for. So you want to convert all these numbers to something on the right here. So here is an image of the fluid field and pressure field around a space shuttle. So this is what you can do. You can take the numbers and go to visualization. And there are some basic data types, and I think we showed them when we discussed mesh generation. So these are directly related. So you have uniform rectilinear data, basically evenly spaced blocks of data. You have non-uniform rectilinear data with this kind of rectangular data was spaced in different spacing. You have curvilinear data, so swept data. We have polygonal data, which we will be using here in this course, which is unstructured mesh. Meshes based on polygons. And you can have those in an unstructured form as well. So you can have a completely unstructured mesh as well. And these are the input to the data. So you have to kind of write your data in these formats and construct them in a way that you can read it in ParaView. There is a lot of documentation here. I provided this slide set for you. There is also a set of tutorials that you can use. I also provided a separate video on how to do the visualization for this course, so in 2D. I will also show this live here shortly. So, and also in the program there is of course a help menu which you can use. So I will start by sharing my ParaView window. So this is the ParaView window. The text is a bit small. I hope you can see it all, but I will try to make it as clear as possible. So you have, of course, the help menu here. If you want to get help, don't underestimate it. There is a lot of information here. There's also some interesting thing. If you want to kind of experiment with visualization, you can go to example visualization here, and you click on one of these here, and you can try them out yourself. So you have some data you can experiment with. One important button here is the reset button here, which resets the session. So there is no new in this. You work with a visualization flow, and it's there is no kind of document. So if you want to kind of start from fresh, you just do reset, and it will remove every part of the visualization here. So the user interface, you have a menu bar here with all your tools. You have of course your toolbars which you can move around which you want. There is a pipeline browser, and the pipeline browser is where you load your objects into. So you load your visualization or your grids in here, and then from there you can add more operators to this to refine your visualization. You can cut it, and you can So in this here, you will create your flow. And down here, you have a properties toolbar or properties field where you can, when you select objects in your flow, properties for these objects will come up here. So just to kind of create something simple, we can go to the sources here and create a simple geometric shape that we can render. So geometric shapes here, and we render a cylinder. One thing to notice as well, ParaView is not an application that displays data directly on the screen, because sometimes when you load data into ParaView, they are really huge, and you don't want to render them until you have set your properties. So you have to kind of force it to display data on the screen. So you can see when I loaded a cylinder here, the apply button was highlighted here. So when I press apply here, it will render a cylinder. So now I can, with my mouse, I can move around this object here on the screen. And you see also now that when I selected the properties here, the properties menu was populated here. So here I can, for example, change the number of facets on the cylinder here. So now it's more detailed. I can go down a bit like that. I can also change the height, for example, to 2, and then you have to press apply again. And you see I have a longer cylinder here. Every time you change a property, you need to press the apply button. You can also change the color of an object here. So coloring here, it says a solid color. So I can edit here and I can select any color I want. Okay. And you see here. I can also change, there is a display properties here. I can change, for example, specular lighting, which is how kind of glossy it is or how shiny the object is here. So the cylinders, this is kind of not a really serious data visualization example, just an example how you use the normal interface here. And if you wanted to change the views here, you have also a view menu here. So here you can reset the view. You can zoom to the data. So it's kind of, if you have zoomed out here, it will kind of focus on your current data here. You can also switch which axis you look at objects from. You can rotate it in different directions. So here you have all the basic view controls. So let's see here. We do a reset again. So of course, when you do visualization, you probably will load data from disk. And one thing you will notice here is that there is a lot of data types supported. So if I go File, Open, and if we look at, you can see here, this is the supported formats you can load from in ParaView. So there are a huge number of formats. So most visualization formats are available to load. So what we're going to do now is just to kind of load a simple example here. So this is a cylinder simulation here with which has a heater in the bottom, so it will display a heat field. So what we can do then is we select all the variables here. So in this list here, you see all the variables contained in the model, which we can display and visualize. So if we just select all the values here, so we make sure that we have them all, we click apply. So now you see here I have a cylinder of some sort here, but it's kind of gray, so it doesn't show any values yet. And you can change the data representation here in different ways. So one important thing is you have, so now we are seeing the surface representation. We can also look at the points of the model here. We can look at surface with edges. So here you see the finite element structure. You can see only the wireframe here. And you can also just show the outline of the object. So in certain cases when you have really large models, it could be beneficial to just show the outline of the structure. I'm going to put the surface again here. So what we want to do now is, let's see here. Yeah, you can. So now we have not mapped any data to this structure. So what we can do here is look at the temperature. So here you see I have a temperature variable here. Oh, no, it was a bit. Yeah, you can see. Okay, so the temperature outside here is, so there is a heater here below, which is heated up here, and you see here that there is a temperature inside here. So problem is that we can't see this. So we need to kind of try to slice this here so we can look inside of this. And what we can do then is we can use the filters here to slice the object. So, and you see here there is a lot of filters available, which can handle data in different ways. You also have some of the common ones here, which provides you with some shortcuts to these filters you can apply your objects. So let's see if we apply a contour filter here. And we say ISO surfaces to 400. Temperature. And we set contour to 400. So now you see you get the contour line here where we have the temperature is 400. So now we want to kind of create a cutout surface as well. So we will slice the model and look inside of it. Then we select the main model here again. So now with this surface here we show here is the contour here. And now we will create a cutout surface here with the clip tool. So we select clip here. And here you can see now here it asks you for a clipping plane. And we uncheck, we will just uncheck this so we don't show the plane here, and then apply. Now you can see here that we have cut the model in two. We still show the cutting the ISO surface here. What we can do here to make sure to show the model a bit more, we can select contour, and we can make it a bit transparent. So opacity here can change the transparency of a certain visualization. So in this case here, you can see through the visualization here. Let's see here. You can also do something called streamlines, which is to follow the flow. So let's see, we remove this one here. We don't delete that one. Oh, I deleted the wrong one. Let's see here, we do delete again. We do a cutting plane. apply, and then we click off this one here. So, and now we want to have streamlines, so we add a stream tracer, and seed point to source. Now you can see here that it shows you how I did it wrong here. Let's see, we'll start again here. Like that. So it depends. So there's only the final flow here will be shown. So what I did wrong now was that I continued on the clip here. I want to create streamlines from the top level here. So let's do that again. Point source. We unclick show sphere and apply. So now here you can see the streamlines here that it emits from a point source here. So you can see that they're visualized like that. So what we also can do is that's basically we can change, for example, the stream tracer to use lines instead. Okay, so now we have this. Now we want to. So perhaps we don't like the color scales here. We can edit that as well. So we go back here to our clip plane. And then we edit here coloring. It says now it colors from the temperature. So we can edit here. Oh. And we can do, if we click on, there's a small heart here. And we can click here to change the color scheme here to Inferno. And now you see here that the color scales, the color was changed. You also see here it adds a coloring scale here below. And you can change the properties of this one as well. So here you can say I can orientation horizontal instead to the color scale. Okay, we can move that. You can also add for the model here. You can add axis here, so you see the scaling of the model. So this is basically ParaView. Now you will probably do a bit simpler models, which I will also illustrate here. So how do we get our models into ParaView? So I will, let's see here. I will reset this first. Yes. So I will just try some different, some simple examples here. So you will use a special module, a library or module in Python called pyvtk. It's shown here in the code. This is how you import it. And this module provides a set of classes that helps you generate the input files required for ParaView. So ParaView has a standardized format called VTK. So the extension is VTK, which you can generate with the pyvtk module. So in this case here, I have this is not a final element. This is a elevation file of a mountain in Colorado. So this is a binary file we load here, and we convert that to a NumPy array. Then we convert it into a 400 by 400 array. And then we do just show it as an image. But the main work here is done below here. So the first thing you do is you create point data. So in this case here, we put the X array here as point data. This will be our grid. And then we create something called a Pyvtk data structure, where we add structured points. That means that we have a structured 2x2 grid by 400 by 400 data points. And then we add our data points to this data structure. And then we do data to file, which will write elevation.btk file here to disk. So let's see if I can run this and hope it will work. So this is the image of the image data we read, elevation data. And then it wrote, let's see here. It should write something called elevation data. Yeah, here. So elevation BTK. Why didn't it write it to? I'm a bit confused because it's, let's see here. Okay, it's okay. It was just my browser that didn't update it. So now we can load this into BTK. So let's do that. ParaView. So we open here. We go to BTK. We have our elevation data here. Okay. Apply. So now I see we get just a empty we need to switch to 3D as well. So I see it's a flat square. So what we can do is we can of course change the color scheme here to be something else. What we also can do is we can magnify or create a surface here to create kind of a 3D model of this. So that's here. So there is a lot of filters. So to find filters, you can search for them. So scale. And what we are aiming is warp by scalar, this filter here. And what we can do with this is we can apply a scale factor and apply that to this one model here. And now you can see here that the model is 3D. What we also can do is we can set the specular lighting a bit more. We can kind of get a more cool effect of this. So this is one way of getting something out from Python. So let's give another example. The next file here is here we'll also do simple. This is just generating noise. I think it's the same as before, so I can skip that one. But here I generate noise in 3 dimensions. So basically 128 by 128 by 128 points, a grid. And then I have the size here is 8 by 8 by 8. And then I generate point data. I rescale my noise. I write the data to point data, and then I read it in. So I do Pyvtk here. run this. Okay, I'm missing one point. I skipped that. It's not so necessary. We do have some other examples here. So you can create data from scratch in the pyvtk. So here you see that you have the structure here, points, polygons. I can specify point data. So you can specify scalars that you want to provide to different points. You have here is a lookup table to kind of color the different points. Cell data is data that is connected to the element. So if you have one polygon, you can connect data to the points in polygon. You can also connect data to the cell itself, or the polygon itself. So in an element, for example, if you have a flow in the middle of an element, that is cell data. You can also have, for example, von Mises stress that is for the entire element. That is also cell data, right? If you have temperature at the nodes, that is point data. So you create point data, cell data, and then you combine it to VTK data. So you have your structure that defines the mesh. You have point data that defines the data on the nodes. This is here. And then you have the cell data that is data for each cell. So let's see here if we do. So let's see here what we get. So this was example 1. So this is a very simple cube with data in it. So you see here you have scalars, cell data, and we can display cell data. So this is the polygons are the surfaces of this cube. So those are given specific colors each of the cells here. So this way you can import data and you can create any data that ParaView can visualize. Here we have a structured point data structure. So this is a 3x4x6 grid, and we just provide point data to each of the points here. And here we also you can do function plots here if you want to in different ways. You can create vector. And you can visualize them in different ways here. So let's see what happens if we run this. So we have example 2. You have always to kind of remember to always press the apply here, otherwise nothing happens here. So let's see if we do a wireframe here. So now you see here, this is a 1, 2, 3, 4, 1, 2, 3, and 1, 2, 3, 4, 5, 6 grid. So we can color this by scalar, and we change to surface. Now you see here that we have a solid block here. We can look into this one as well. We can do a cut, show plane, remove, apply. And now we can look inside of it. I think I will go to, so this is also an example of using points and vectors to create a cube or different kind of geometric shapes here. Let's see here. This. Example 3. So this is shows all the elements you can produce in ParaView. So there are triangles, there are polygons, and there are lines and points. So now we have this do a lot of 3. So now we kind of need to see how we can take our own data from our own results here and create a visualization. So I have here a finite element example here of a stretch calculation, and I have created. I have a displacement field. I have a stress field, and I want to create von Mises visualization for each element as well. So what I do now is I want to create the data structures to be able to export to Pyvtk. So I'm just going to get my notes here. So the first thing we need to kind of create is the points, and there is one kind of oddity with Pyvtk is pyvtk is that it doesn't handle arrays. So you need to convert all your arrays to lists, but fortunately it's very easy to do in NumPy. So first we do points equals to ports, which is a data structure I got out from my mesh generation, to list. Next, we need to create our polygons for Pyvtk to visualize data on. The problem is that the topology we have currently is based on degrees of freedom. So I have 2 degrees of freedom for each node, and that is not the topology that ParaView can handle. So you need to have a point node the topology. But fortunately, the mesh object has an additional property that you can query. So if we do polygons equals to mesh.topo -1. So our topology with degrees of freedom are 1 based, and Pyvtk is 0 based. So the topology has to be reduced by 1. That's why I do a -1 here. And then I do to list here as well. It's not the most super efficient way of handling this, but the library is created in that way, so I can't change that. So now we need some additional variables to store other data in. So because the displacement fields, to displace a field in ParaView, you need a vector field. So we need to create a field from our displacement vector and create vectors, data structure with vectors in each row. So we create an empty list, and then we create, I think we can see that one. And then we do for I in range 0 dot. So what we do is the displacement field is there are 2 displacement degrees of freedom, so x and y. So we jump through the displacement vector with a step 2 and create vectors for each of those pairs. And then we do displacement.append np.as I np.as scalar and then ParaView only takes three-dimensional vector. So we need to specify a 0 here for the z-axis. So we only provide a scalar or a vector field with two-dimensional arrays, vectors, but we need to specify as a three-dimensional vector. So we add a 0 here at the end. And then we this point to VTK. Point data is the class that handles the points at the nodes. And then we do VTK dot vectors. And one thing that is important is also you can every data structure you create in VTK can be named. So in this case, I put a name here, displacements. Then you can also find it in ParaView later on. That. And we create scalars, which is our von Mises stresses. So VTK dot scalars. And we have our principal stresses, or we have two vector fields here for principal stresses 1 and 2. So vectors 1. So now we have to create our cell data here. So the cell data that goes in. So point data is the displacement field. So for the stress problem, the cell data is the Mises stresses that we provide for the element, and also the vectors for the principal 1 and 2 stresses. And then we create a cell data structure like this: VTK cell data scalars vector. And now we create a structure. Sorry for my typing today. VTK dot polydata. So we have data polygons, polydata, points, polygons. And then we have our VTK data that we'll export. That is a combination of everything. VTK data, VTK dot VTK data, structure, cell data, and then we write it to disk. And we specify that we want to be ASCII. So you can write them as binary VTK files, but also ASCII files. And ASCII files you can read by using a normal text editor. So let's see, I hope this will work. You can just ignore these warnings here. And now we should have EXM here. So now it wrote EXM6 VTK file. So let's see if it contains our nice stress fields and displacements. So let's open this one. Okay. So let's see what we get by default. Let's see. Something was not right here. I think we missed something here. Let's see, go back here again. Okay, better. I think I missed to, you need these keyword arguments here to specify the correct arguments for polar data. So what it does now, it found our data, so it found von Mises here, and it's by default it shows you a surface plot. So let's see here, we can just do a more interesting rainbow coloring scheme just to show that we can change this. Can do jet like this. We can also apply, so now you get just the von Mises stresses here. And what we can also do here is apply we have a displacement field here with vectors here. So we can warp our mesh by a special vector field. So in this case, we do, it's a special called warp by vector, which we apply to our mesh. We can do, let's see here, we can calculate a good. So now you see it applied our warp, our displacement field to this model here. What we can do now as well, we can do just display another mesh here. Let's see here. So we can display the undeformed mesh here, but just turning this on here, and we can specify a wireframe here instead. So you can see the original mesh here. What we also can do is we can add our principal stresses to this display. So let's see if we turn this off here. So as long, then we do continue on this one here, and we add a glyph field. That is it creates an oriented glyph at the point of the vector field. So glyph type, we take a line. We select our principal stress number 1. We scale by principal and scale by magnitude. So let's see what happens if we just run this here. Okay, so now we have a kind of invalid scaling of our principal stresses. So we need to figure out a more suitable stress. So what you can do is next to the scale factor, there is a reset button here that kind of calculates a good magnifying factor for the data that is in the vector. So let's see here. And then we do apply again. And now you see here we have stress errors here. I think we can reduce them a bit, perhaps a bit more. Another thing here that we probably shouldn't color them in the same stress color, so we change coloring to solid color, so we have them white. And you also see that it doesn't draw them on every element, but we don't have that many elements, so we can actually draw them on every element. So here you can see here, glyph mode, uniform spatial distribution. So instead we say we want to draw them on all points. So now we have principal stresses in every element. So what we also can do here is we can add the second principal stress. Then we go back again here to the warp vector here, and we will add another glyph. And now we change to principle 2, principle 2. Now we have to kind of scale them in the same way we scaled the other one. So we need to pick the scaling factor from the other glyph here, otherwise we get strange scaling here. So like that. Line, and we color by solid color. So now you see we have the other, we have two arrows indicating the two principal stresses of our simulation. So this is kind of nice. You can, if you want to kind of, you can change the transparency a bit so that you can see more of the model here. And we can do that by the other glyph as well, 0.44. So this way you can kind of create your own visualization, and we can add, for example, axis grid. So you have the coordinates here. We can add a transparent grid here. So we color solid color for the mesh, and we do this very opaque. So here you can see the undeformed mesh here as well. So this is a stress problem. Let's see here, we go back here. This is the code you will use to kind of create this file. So I'm just going to bring up another problem type. So I have already pre-computed some of these. So let's see here. So one nice thing with ParaView is that if you name your files with numbering, it will create them as a, you can open them as a time series. So that is what you're going to do in, I think is this one or next assignment. You're going to do a parametric study. And you output one Pyvtk file for each time step or for each parameters range. Then you can open all of them at the same time. So you see here, it will have a plus sign here to show that this is a series. So let's see if we open them here. And then we do apply. So this is your famous groundwater problem. We have one pressure here and one pressure here, and then you have a continuous variation over there. But the interesting thing here is that you have a set of controls up here where you can switch between the different parameters here in this case, or time series if you want that. So here you can see here that I vary the depth of this thing here. I can go back here again. And you see the color scale is valid for all of these parameters. So it doesn't change the color scale depending on which step or parameter you are in here. So let's see if we can do a nice visualization here as well. So first we change the coloring here to, let's see here. That was not so nice. We'll try something else here. Like that. And then I want to show, so what have we here? Now we can see here what data we have in our file. We have pressure, which we have displayed here. This is default. We have flow and we have max flow. So the flow is a vector field, so we can create a glyph from this one. So we do, we want to orient the vector by this one, and we put line, scale array by flow, auto calculate, all points, apply. So they're a bit big, so we scale them. Like that. Now you also see you can scale or create a color scale for the magnitude or the flow here as well. So it create a different color scale here. If you're not interested in that, we can just color, solid color, and then you get just arrows without any coloring. We can also do visualize the max. Yeah. Let's see here. So the max flow is a cell data that is for the max flow in an element, and that's on a single element here. So now we combined, we changed the background here to this instead. And if we go back to pressure again, we get that back again. And now if we zoom out here, you can see that you can loop over this play. And you can see here that the flows are increasing when you kind of make the slit deeper. What you also can do here, which is kind of cool, is that you can save this visualization as a script. So you can save state, and then you say you want to create a Python state file instead. And then we save it as test. Okay. And then we have GV somewhere here. So it created a Python file here, and if we look into that file, we can drag it into So what it creates, this is a Python representation of your visualization. So it creates a lot of objects here. And it loads the data here from VTK, and it sets the properties that we set manually. And this one you can run, but not from Spider. You have to run it from inside ParaView. So if you do like this, you reset, and then we open this state file. Load state, sorry. GV does test, and it will recreate the visualization for us. And this file you can edit manually and create your own customized visualization of this. So this was my introduction to ParaView. I realized today that the link to ParaView, their website was down today. So I provided you with an executable you can download for the Windows part. I didn't think I will check the Mac version as well, but it should be, I will try to get that as well. But hopefully the site will come up shortly again. So you can download and install ParaView on your own computer. So do we have any questions here? So I think the the assignment will go through this in some detail on how you can create your data for the visualization as well. It's not too complicated. I'm also working on 2 routines to create this automatically from Colfem, but I'm not really done yet here. So, but it's good to have this to go through the object model and create the data from pyvtk. You can use that in different types as well. So otherwise, I will end this lecture now, and we will see you tomorrow morning at the exercise, and you can ask more questions there if you want as well. So I will try to render this video here and put it on the website as well shortly. So, okay, see you tomorrow then.